Hey class, Mr. Moyden here with a little lesson to help continue our discussion on derivatives and differentiability and how we can better understand the way functions behave. So just a bit of review before we get into how to make a function differentiable. Remember that the word differentiable means that a function has that property at a single point if, one, it's continuous at that point, and two, at that point you have a unique tangent line with a defined slope. So remember, it has to be continuous. And as a second condition, it has to have a unique tangent line, which means there's no ambiguity. You can't have a corner like this where the tangent line could be negative or it could be positive at that point. And it has to have a defined slope. The opposite would be an undefined slope, which would be a vertical tangent. Right here, you'd have an instant where it's exactly vertical. So that would also be non-differentiable right there. So in terms of algebra, how does it look like? Essentially, a function is differentiable when both the original function and the first derivative are both continuous. So if you have this criteria met, then essentially you have differentiability, the function and its derivative. So that being said, let's see if we can use this basic fact to figure out how to make a particular function so that it is differentiable, so that it's smooth, essentially. So the question here says, as many of them of this type would, find the values of a and b, or constants a and b, to make the function differentiable. And you're given the piecewise function. It looks like a parabola is going to meet up with at the point at x equals 1 with some kind of cubic function. So the first thing to do is to establish the continuity of f. So remember, continuity is a requirement. It's not sufficient by itself, but it is necessary for differentiability. So we're going to use the definition of continuity to make sure that this function is indeed continuous. So remember, the definition of continuity at a point like x equals 1 would be the limit as x approaches 1 from the left of f of x is equal to exactly f of 1, which should also be equal to the limit as x approaches 1 from the right of f of x. So in practice, that means if you notice the function here at the left of 1 and exactly 1 are the same function, so these two are going to be the same anyway. The question is, how do we make it the same as 1 from the right? So if I plug 1 from the left in, I'm going to use the top function here. So if I plug 1 in, that's 3, 1 squared plus 4 times 1. And that should give us 7. Same thing for f of exactly 1, because they're the same function. And 1 from the right, we've got to be careful here. It's going to be 2 times 1 cubed plus some number b times 1 plus some other number c. So essentially this is telling us that 2 plus b plus c needs to equal 7. So this fact must be true, this is already true, in order for continuity to occur. I'm going to rearrange that slightly. If 7 equals 2 plus b plus c, that implies that b plus c have to equal, if I subtract 2 from both sides, 5. So for continuity to occur, b and c have to equal 5. But of course, there are infinitely many pairs of numbers b and c that add up to make 5. 4 and 1, 2 and 3, 0 and 5, and many, many others. So to get a second equation in order to figure out differentiability, we need to take the derivative of the original function and figure out, is it continuous? Is there a smooth transition in terms of the slopes, which is what the derivative describes? So keep in mind that if the original function is a piecewise function, it only follows that the derivative will also be a piecewise function. So f prime is going to equal the derivative of each piece. So using the power rule here, you get 6x plus 4, and that's valid when x is less than or equal to 1. And on the other one, you get, once again, I've got to be a little careful here, you got 6x squared plus bx. Keep in mind, b is a constant, so just some sort of number times x, and the slope would just be that number. So 6x plus b, and then c is a constant, so its derivative is 0. So 6x squared plus b is the derivative of this piece right here, and that's valid when x is greater than 1. So a function is differentiable when the function and the derivative are continuous, so we do the exact same operation with left, middle, and right, approaching and exactly, and approaching again, but this time with the derivative function. So all we do, you take the limit as x approaches 1 from the left of f prime of x this time equals f prime of 1 equals the limit as x approaches 1 from the right of f prime of x. If this is true, then the function is continuous, the derivative therefore is continuous. So once again, these two refer to the same function, exactly 1 and less than 1. So if I plug 1 in, I get 6 times 1 plus 4 in both cases. And that gives us, of course, 10. For the right-hand case, if I plug 1 in, I get 6 times 1 squared plus b. So that means that 6 plus b must equal 10. Well, if 6 plus a number equals 10, subtract 6 from both sides, and without too much of an effort, you know that b must be equal to 4. And all of a sudden, it makes our work a little clearer. Now, sometimes you'll have to solve a system of equations when you get here, and theoretically, this is a system of equations. It's just that one of the solutions is pretty straightforward, and then the second solution becomes that much more obvious. But you can think of this as a very rudimentary form of substitution, right? Normally, it's in a more algebraic case, but in this case, b equals 4, b plus c equals 5. So if b plus c equals 5 and b equals 4, that of course implies that c is equal to 1. So we have found the values of, I should have said b and c, not a and b. I just realized my snafu there. Let me quickly fix that. There we go. So we found the constants that make our function differentiable. So keep in mind, one thing I've neglected to mention earlier on, besides this little mix-up, is this thing is a continuous differentiable, just a standard parabola everywhere. This is a nice smooth cubic function everywhere. The only question is, do they hand off at a continuous way? Well, if b plus c equals 5, they do. Well, do they hand off in a smooth way, even if they do meet? Well, if c is equal to 1 and b is equal to 4, then you sort of guarantee the differentiability as well as the continuity. So let's do one more example in the same vein. This time the question says, find the values of a and b, and I had the letters this time, correct? That's good. Find the values of a and b to make this function differentiable. It looks much the same as the previous one, but a couple of major differences. You'll notice the handoff point is different, so most of our limit investigations will be different. And likewise, the variable for the constants, a and b, the terms we're looking for, are sort of in different locations than they were last time. So once again, this is a parabola, always differentiable and continuous. This is also a parabola. The question is, do they meet and do they hand off in a connected and in a smooth manner? So establish continuity. So continuity at x equals 2. And remember, we're first investigating f. Is f continuous? At x equals 2. So the limit as x approaches 2 from the left equals the exact value at 2 equals the limit as x approaches 2 from the right. Once again, left and equal to are the same functions, so to save ourselves some work here, these are the same anyway. So you plug 2 in, you get 4a plus 10. It's very easy to mix up your a and your x squared. Remember, x is approaching 2, so we square the 2, and the a just comes along for the ride, plus 10. That needs to equal the other side, which is from the right, which is this function here. We get 2 squared minus 6 times 2 plus b. So this would be 4 minus 12, which is negative 8. So 4a plus 10 is equal to negative 8, and we have this plus b as well. So solving, or rather to get this into a little more familiar form, if I gather my variables on one side, 4a minus b equals negative 18. So not quite as straightforward as b plus c equals 5, but nevertheless, this relationship must be true in order for the function to be continuous, which is a requirement, but by itself is not enough, because you can't solve that by itself. You need a second equation. So now let's check f prime's continuity. Is f prime continuous at 2? Because if so, if f prime is continuous at 2 and f itself is continuous at 2, then the function, therefore, is differentiable. So quickly taking the derivative here, once again, it's also going to be a piecewise function. The original function is right here, so let's see. Once again, I'm going to be careful with the a. The a is a constant. The derivative of x squared is 2x. And since that's sort of like a coefficient, it'll be 2 times a times x. And the derivative of a constant like 10 is just 0, so we get 2ax, and that's valid in these cases. Over here, we have x squared minus 6x plus b. So using the power rule, that becomes 2x, constant multiple, or mx, if you want to think of it that way, 2x minus 6. And then b is just a constant. Its derivative, its slope is 0 because it's not changing. So 2x minus 6, and that's valid when x is greater than 2. Once again, the limit definition of continuity says that the limit from the left of the function, which in this case is a derivative, must equal the value at exactly 2, which should equal the limit as x approaches 2 from the right of the very same function. These are the same again. Plug 2 in, and you get 4a. Just making extra care there, don't mess up. 2 is x, right? So 2 times a is 4a. That's also true for this case, so these are both 4a. The question is, what's on the other side? You plug 2 in, you get 2 times 2 take away 6, which is 4 take away 6, better known as negative 2. So 4a is equal to negative 2. Well, there's only one variable here. There's only one number that makes this true, so divide both sides by 4, and you have a is equal to negative 1/2. So substituting this value back in, or the first equation here, we have 4 times negative 1/2 minus b equals negative 18. That will give us negative 2 here minus b equals negative 18. If I move this b over here, it becomes positive, and add 18 to both sides. That gives me 16 equals b. So now we have the two values of one of a and one of b that make our function not only continuous, but also differentiable. I can zoom out here a bit so we can see both. Continuous and differentiable. And keep in mind, the word differentiable implies continuity, right? You can't have a differentiable function if it's not continuous, so this allows us to solve a two-variable equation because we have two equations. All right, I'll see you in class.